In this set of notes, we're going to look at limits at infinity. So previously in section 3.1 of the textbook, we looked at several different limit rules. And you'll notice that for each of these limit rules, we were looking at when x approached a constant. Well, it ends up that each of these limit rules will also hold if we look at what happens when x approaches infinity. And so we're going to look at several different examples. And in particular, you'll find that the fourth rule is going to be the one that is the most useful when we're looking at limits as x approaches infinity. All right, so for example, suppose we wanted to find the limit of this function right here. And again, notice we're looking at the limit as x approaches infinity. So at first glance, this may seem fairly complicated, but we can use our limit rules to help us. And so notice in the fourth rule, what we have here is if we're looking at the ratio of two different functions, then what we can do is look at the limit of the numerator over the limit of the denominator. And so let's go ahead and set this one up that way. So here we know that the limit as x approaches infinity of 1 over 2x plus 1 divided by 3 minus 1 over 4x, well, that's going to be equal to the limit as x approaches infinity of 1 over 2x plus 1 divided by the limit as x approaches infinity of 3 minus 1 over 4x. And then further, notice that here in both the denominator and the numerator, we have addition and subtraction. So really, we can go ahead and then apply rule number 2 to break that up and look at the limits individually. So further, and I will say that most of the time when people do these, they won't necessarily explicitly write out each of these steps, but I think it is good to see that these are coming from, these limit laws or limit rules. All right. So looking at the first term here, notice in the first term we have 1 over 2x. So we can easily see that as x approaches infinity, that x is going to get incredibly large. It's in the denominator, it's in the denominator. And so this piece right here is going to approach 0. Looking at the next piece, we have the limit as x approaches infinity of 1. Well, the function 1 doesn't involve x at all, it's just a constant, so it's not going to change. Similar in the denominator with 3. And then finally, this last piece here, again, we've got x in the denominator, so 1 over 4x. I apologize for that noise. So in this last section, again, we've got the limit as x approaches infinity of 1 over 4x. X is going to get really, really large. It's in the denominator, so that term is going to go to 0. So notice here, by using the limit laws, and we break this limit up into smaller pieces, it's really not as bad as it initially looks, and we find that that limit is equal to 1/3. So we're going to look at another example, but before we do that, let's talk just a little bit about the previous example. So notice in the previous example, one reason that that fourth law was so useful is really what we were doing is we were looking at a ratio of polynomials. And if we look now at this example, notice we've got the same thing. We've got a ratio of polynomials. And so it ends up that ratios of polynomials will follow certain patterns. And so example 2 in your text for this chapter looks at 3 different examples. We're just going to look at one here, but I highly recommend to go back and look at all 3 of those examples compared to one another. And what you're going to see is when you're looking at a ratio of polynomials, the behavior of the limit is really going to be determined by where the leading term is. And so what do I mean by that? So notice in the numerator, the leading term is x to the 3rd power, whereas in the denominator, the leading term is x to the fourth. So here, for this particular function, the highest term is the x to the fourth, and that term is in the denominator. So where that highest term is, whether it be in the denominator or the numerator, or it could be that the two leading terms are equal to one another, that's really what's going to determine the behavior of the limit. So let's look at this example where the higher leading term is in the denominator and see what we end up getting for the limit. And what you're going to find is, since that leading term is in the denominator, that means that the denominator is going to grow in size at a higher rate. And because of that, since the denominator is going to get larger and larger quicker, we're going to see that this limit actually goes to 0. So let's see how to do that. But to start out with, to make it easier for myself, I'm going to take that highest term, which again is x to the fourth, and I'm going to divide all of the terms by that x to the fourth. So here we've got the limit as x goes to infinity, 3 minus 5x cubed divided by 1 plus 3x squared, or 3x to the fourth. And then again, what I want to do is I'm going to divide each of the terms by the largest term. And so we're going to have 3 over x to the fourth minus 5 x to the third divided by x to the fourth, 1 over x to the fourth plus 3 times x to the fourth over x to the fourth. And notice, since I'm dividing each of the terms by x to the fourth, I haven't changed the overall value. All right, so now notice that this is equal to the limit as x goes to infinity. We're going to have 3 over x to the fourth minus 5 times 1 over x divided by 1 over x to the fourth plus 3. And now notice that we've got something that kind of looks like that first problem that we looked at. Each of our terms has x in the denominator, and so now we can use those limit laws. In particular, we're going to use limit law 4 and limit law 2, really even limit law A, and I'll show you our first one, how that's coming into play, to now evaluate this limit. So notice that this is equal to the limit as x goes to infinity. And I'm going to look at this first term. And here I'm going to have 1 over x to the fourth times 3. So notice the 3 can actually come in front of the limit because of the first limit law. Minus 5 times the limit as x goes to infinity of 1 over x. All divided by the limit as x goes to infinity of 1 over x to the fourth plus the limit as x goes to infinity of 3. So in the numerator, notice that this is going to be equal to 3 times the limit as x goes to infinity. Well, we've got x to the fourth in the denominator, so that's going to go to 0. So we have 3 times 0 minus, very similar argument, 5 times 0 divided by 0, and then notice this term doesn't involve an x, so it is just going to be 3. So this whole expression is 3 over 0, and so we find out that the limit is equal to 0. And so again, the example in your textbook looks at 3 different examples. We've got where the denominator has the higher term, and you're going to see that it goes to 0. You're going to see that when you've got the higher term in the numerator, it's no longer going to go to 0, and then when they are both equal to one another. And that leads us really to these 3 rules for limits of rational functions where we have that ratio. And so here, if we have 2 polynomials, p and q, and we're looking at their ratio, notice here that if we look at the leading term for both of them, so if the leading term has m for p and n for q. So all this is saying is, just for example, let's say that we were going to look at 3x squared plus 1 over 5x cubed plus x. what we're saying here is in this case, p to the x would be the one in the numerator, q to the x would be the one in the denominator. And so for p to the x, the m in this case would be 2. And for q to the x, the n would be the 3. So really, again, all it's looking at is the leading term in the numerator and the denominator. So in the numerator, this is going to be m, and the denominator, this is going to be n. And then what all of this is saying is to find the limit, it's really going to depend on the comparison of that leading term in the numerator and the denominator. So if we find that m is less than n, and let me erase this. So notice here, if m is less than n, what that really means is the denominator is higher. You're going to find that the limit is equal to 0. And that's what we just saw. If it ends up that the numerator is higher, and again, this is the power of the leading term here, we're going to find the limit doesn't exist. It's going to go off to infinity. And then we're going to find out that if m is equal to n, that you're going to have a limit, and it's actually going to be equal to the ratio of the constant that is in front of those leading terms. And then if the limit's divergent, so in other words, we're in this case right here, we may want to know if it goes to positive or negative infinity, and here are the rules for that. And so again, your textbook looks at 3 different examples where you can see all of those. All right, and so then last one here, we're just going to look at one more example of a limit where we're going to apply some of those limit laws. You're going to look at a homework problem that is very similar to this one. And so this problem is going to look at what is called logistic growth. And so here, suppose that we have the size of a population at time t is given by the following function. And let's say that we want to determine the size of the population as time goes to infinity. So let's see how we could do this. So notice we're interested in the limit as t goes to infinity of nt. And that's equal to the limit as t goes to infinity of 50 divided by 1 plus 6 e to the negative 2t. And we can apply all of those limit laws that we've been seeing. So we've got the limit as t goes to infinity. Oops. Didn't mean to do that. There we go. Of 50 divided by the limit as t goes to infinity of 1 plus 6 times the limit as t goes to infinity of e to the negative 2t. So notice in the numerator, if we take the limit as t goes to infinity of 50, well, 50 doesn't involve t at all, so that's just going to be equal to 50. Divide it by, well, the limit as t goes to infinity of 1 is just 1, because again, it doesn't involve t. Plus, in the next term, we have 6 times the limit as e to the negative 2t. Well, remember, if I just kind of write over here, that e to the negative 2t is equal to 1 over e to the 2t. And we know that e to the 2t as t goes to infinity is going to become incredibly large, so that entire term is just going to go to 0. So we end up with 50 divided by 1, or just equal to 50. And so that would be the size of the population as t goes to infinity. So that's going to conclude this chapter 3.3 notes. As always, if you have any questions, please let me know.